Yeah, hi everyone. I'm Nisha. I'm a PhD student at UCL, and just a nice picture of UCL. I normally work for the Atlas detector with machine learning on tracking, particularly within the pixel detector. And today I'm going to be presenting GNNs, pattern recognition, and fast track planning. So to give a quick outline, the main part of the talk I'm going to focus on is the algorithm, the sort of development and the different stages of it, and that forms the main bulk of today's talk because we are still in the very preliminary parts of the results. And then I'll move on to present some of the results. One on the application of the GNN algorithm to Monte Carlo twin model, and the second on to the TrackML model as well. And then I'll conclude with some ongoing and next steps. I think.
On the screen?
Yeah, it's not quite.
No.
It points into a
It's
strange
like-
mode.
Oh, I screwed up. That's
Yeah.
a little bit too fast before.
You may have to reshare it, huh?
Mhm.
It
It does take the screen.
Yeah.
Yeah.
Yeah. Okay. Yeah. So at its core, track finding is a pattern recognition problem. It is to associate measurements, which are known as hits into sequences, and reconstruction of charged particle trajectories is one of the most computationally intensive tasks within energy physics. And this can be particularly problematic for particle detectors, such as the high lumi LHC, as detectors go into upgrades where their luminosity and pi depth increases. And this really creates a huge demand for computing power. So this gives us the necessary motivation to find novel approaches in track finding and help to improve our savings in CPU. So we know that a lot of modern silicon detectors typically consist of several types of sensors, which are the pixel and the strips. And here we focus our GNN application on the pixel detector. And the GNN algorithm serves as a more sophisticated seeding for pixel clusters, which will form preliminary track seeds, which can then be defined and extended into the strips. And hopefully such an approach could be very efficient, saving computational resources if the GNN doesn't produce too many fake tracks. So to give you an overview of the algorithm, essentially it is to iteratively resolve ambiguities and mask incompatible edge connections in order to improve track parameters. And this is a really unique approach whereby we use Kalman filters embedded within the GNN for two main purposes, which is for information propagation and track extraction. And it is unlike the more sort of traditional approaches where multi-layer perceptrons are trained. So to walk you through the algorithm then, the first stage is to obviously initialize the GNN, and then with the nodes and the edge connections, it pairs. And then we apply a sort of out-of-the-box connected component analysis to initially separate the GNN into smaller, more manageable subgraphs. The first iteration is then a Gaussian mixture reduction, GMR VO clusterization. So this is where we sort of model a node and its neighborhood of edge connections as a mixture of Gaussian components. So each edge, each hit pair connection is modeled as a Gaussian. And then as we have a mixture, we try to reduce this mixture by masking any obvious outlier connections via a clustering algorithm. The second part of the algorithm is then information aggregation and KF update, Kalman filter update stage. So this is really where we harness message passing, message distribution within the network. We then would extrapolate the states between a node and its edge pairs. And then if the state is compatible, we would apply a Kalman filter update there. And then the third stage is network update. So this is where if there's been any changes within the network, so edge connections become deactive or active, we need to reweight components and update our network state and track state vectors. So after each iteration, then we apply the Kalman filter for track extraction, and we see if we can extract any potential track candidates from our graph network structure. And overall, then, it is a fully iterative pattern recognition problem where the GNN tries to learn track parameters throughout the iterations, and the local track orientation becomes more precise. So just to emphasize again the importance and the unique sort of setup of the implementation of Kalman filters within the algorithm, it's central in two parts of the algorithm. So one is for the iterative information aggregation stage, and the second is for track extraction. And the Kalman filters here are implemented using a Python package called filterpy. So for the iterative information aggregation stage, here we model our segment, so a node and its hit pair, as straight lines. So the only process noise that we have within this Kalman filter at this stage is due to the vertical scattering. It's a very simple Kalman filter, and as it affects the track inclination variable. However, in the track extraction stage, the overall track bends due to the presence of the magnetic field, and at the extraction, we consider the overall track. We're not just looking at the individual segment. So we need a more sophisticated process in order to model the Kalman filter. So this is where we use the OU model, the Ornstein-Uhlenbeck process. And this is actually used as a type of correlated noise, and it represents the constant drift in track 5 caused by the presence of the B field. And this basically means that our Kalman filter now becomes 3-dimensional, and the process noise is a bit more complicated. So how do we initialize our network? So we start off by looking at 2D network and extracting straight line tracks. So given a node A conditioned on its neighborhood of node B, we form our track state vector X, which is made up of just the measurement Y and the track inclination T. So we just look at the position of node A and in the direction of the next one, where it's literally just dy by dx. So this forms our track state vector Y, and then we derive our covariance from this as well. So the track state vector X and the covariance C together form a Gaussian component, and then for a given node A and all of its neighborhood connections, we have a Gaussian mixture here. So each connection also has a bidirectional edge weight associated with it. So that indicates whether the edge is inactive or active. Also have a mixture weight associated with it, and this is used in later stages that I'll talk about, and also a prior probability, assuming that a track can produce at most one hit per layer. So then once we've set up our network, once we've initialized it, start with the Gaussian mixture reduction, which basically the main aim of this iteration is to identify and mask outlier edge connections. So for any given node, the number of edge components can quickly rise, and this can be quite problematic. So this is why we have a sort of preliminary screening procedure whereby we sort of reduce the any obvious outlier edge connections, and you can see that in this sort of illustration here. So the kind of local track orientation is towards this sort of direction, and we would expect our algorithm to identify this connection here as an outlier, and you can see that here. And these connections would remain for further iterations. So how can we do this preliminary sort of clustering, preliminary masking? So we do this via clustering algorithm, and it's based off of the k-means clustering algorithm. And we essentially introduce a distance metric between all edge connections, which is known as the Coolbach-Lübler divergence measure. So this distance metric serves as a sort of cost function, and it's a threshold for saying, okay, this edge is going to be within our cluster or not. and if it's not, then it's an outlier, and we can mask it. And the optimal KL distance was learned using a support vector machine SVM classifier, and that was trained separately to this GNN, and the results from that was fed in with FastLookup. So the second iteration then is information aggregation and Kalman filter update. So again, given a node A and its neighborhood of connections B, we would extrapolate the state at B towards A using the measurement matrix H. And it's just a normal linear extrapolation. So our model is a very simple linear extrapolation. We would then validate whether this extrapolation is compatible or not. So this is where we would compute the residual of that extrapolated state and the measurement here, and compute the chi-squared distance between the two. If that chi-squared distance is below a certain threshold, again, we then perform the Kalman filter update, and we say that this connection is compatible, and the vice versa as well. So at this stage, we really harness the sort of message passing, message distribution between a node and its neighborhood. We then would extrapolate the state, validate it, and then perform a Kalman filter update. So the state extrapolation here can be seen here with just a normal linear Jacobian, and its covariance is just the symmetrical product with the Jacobian with the previous covariance, but also including the process noise term here, which is modeled by the OU process that I mentioned. Okay, so after we've done all that, obviously the network is going to evolve and it's going to change. Some connections are going to be deactivated and masked, and some will remain active. So that's exactly why we need to reweight the mixture components and sort of narrow down our local track estimates and improve our uncertainties. So the way that we would reweight the mixture is just with a normal measurement likelihood given by the Gaussian normal likelihood. We would just use a very simple calculation for updating the weights. So this would just be the ratio of a given weight with the likelihood and a prior probability as well, divided by all of the weights. And we also need to account for the number of layers in the neighborhood. So we need the probability that a track passing through node A would be detected at layer L. So this is why we need to divide by the number of layers on either side, because there is a local track direction. Okay, so after each iteration, we can check whether it's possible to extract any track candidates. And this is this kind of track splitting stage forms part of the iterative process, because we can iteratively try to extract any good track candidates. And of course, some remaining networks and isolated nodes will remain, as not 100% of ambiguities can be resolved. So we need to define some criteria for a good candidate, and the criteria that we define is very similar to what criteria is defined in the TrackML competition. So our tracks need to have at least 4 hits, so no track fragments. There should be also at least 1 hit per layer, so no competing and intersecting tracks, and no holes. And the p-value acceptance threshold must be significantly higher when we calculate the chi-square distance using the KF track fit. So the track splitting, the track splitting algorithm comprises of 3 parts. So the first thing we would do is apply out-of-the-box connected component analysis again to separate any of the subgraphs. The second bit is the Kalman filter track fit. So again, iteratively predict and update track parameters. And at this stage, if any track candidates are not extracted here, we would then do a further stage and apply a different algorithm known as community detection. So this is a technique whereby this is a further division of a node set using another distance metric. And I don't have time to talk about this now, but I do if anybody's interested. And here are some examples of extracted candidates. So within these sort of subgraphs here, we would see this purple, green, and this blue graph here taken out using the Kalman filter. But this one here, where we have two nodes in one layer, this would be passed on to community detection. Okay, so moving on to some results. So first, I'll start off with the toy model and the results for the toy model. So we initialized the graph network using 7 different tracks, and it comprises of 70 nodes. So this was just a very simple simulation using the Python package network X, and again the Kalman filters implemented using the Python filter py. The ground truth of the nodes can be seen here, and the edge connection hit pairs can be seen here. And the predicted edges were formed using a very simple hit pair predictor. So the first thing that needed to be done here was to create a framework that sort of automatically determined a suitable region for initiating this pattern recognition. And the criteria that was used for this was the variance of edge orientation for any given node and its neighborhood. So here's a good example of this. I don't know if you can see this very well, but essentially each node is like a heat map. So the white nodes and the yellow nodes show very dense regions where there's many connections, and these nodes have a high variance of edge orientation. And it's very difficult to kind of detect and determine where the local track orientation is because of the fact that these regions are very dense. So we kind of ignore this region for now, and we focus on the cold region where the nodes are in red. And that basically means that it has a low variance of edge orientation, and it's easier to resolve ambiguities and find your local track parameters and local track orientation there. So that's where we begin our pattern recognition. So taking this part of the network, so applying, this is an example of a simulation and applying the iterative algorithm. So the first stage is the connected component analysis onto that network. And you can see that the connected component analysis has done a bit of work for us. It's separated the network into 2 main subgraphs, the orange and the blue, where it's sort of particularly very dense in this region. After the first iteration, so the Gaussian mixture reduction and clusterization, we can see that some of these edge connections have been deactivated. So we're supposed to be in gray, but it's you can't see them here. But yeah, they've been deactivated, and you can no longer see these edge connections here. So overall, on this simulation, the precision with respect to Monte Carlo truth, the precision of outlier edge connections identified was 65%. So it did quite well during the first iteration. And then applying the track splitting after the first iteration, we see that 7 out of 6 tracks were successfully extracted, and a remaining network here, which was to be further processed in later iterations. So this is a second example, again, another simulation on the toy model here, where we see, again, the CCA has done 2 separations of simulation, and after the Gaussian mixture reduction and clusterization, we see some of these connections have been grayed out. And then applying the track splitting onto this, we see that this successfully extracted seven tracks here with a small remaining fragment at the top. This is a result after applying both iterations 1 and 2. So you can see during the first iteration here, after the clustering. So some of these edge connections are sort of grayed out, and you can see that there are many different subgraphs now. So after iteration 1, we were able to extract 5 graphs with a remaining network here, and then after iteration 2, we could successfully extract all 7 candidates here within this toy model. Okay, so you can see that the setup works pretty well with a simple toy model, but now let's look at a more realistic detector model, which is the TrackML setup. So here again, so the GNN algorithm is really for sophisticated seeding within the pixel detector. So the first step here was to focus on pixel NCAT volume. So we just look at region 7 for now. And this is because the sort of geometry in the setup is very simple, and it gives us a nice parallel set of layers to look at. So we again initialize our network of nodes, this time with approximately 9,000 nodes and 13,000 edges, and they're bidirectional. Okay, so this was the initial results with the TrackML setup on the NCAP. So this was a very naive sort of implementation of the GNN algorithm that was built for the toy model applied directly to the TrackML setup. So here you can see the CCA applied to the TrackML setup, and it formed a set of 500 subgraphs that were more manageable than one connected network. And then we applied our GNN algorithm to this. So after iteration 1 and 2, we only saw a very small amount of tracks extracted. We only saw 130 out of 500 tracks extracted, with many of the sort of near vertical tracks not extracted. And this is actually for obvious reasons, because of the fact that our track state estimate is formed of the Y measurement, but also the gradient, so dy dx. And within these near vertical tracks, our dx tends to 0. So that basically means that propagating that through, we see a lot of singularities in Kalman filter matrices. So this was as expected. So how can we combat this? Well, we leveraged the rotation symmetry of our system, and we rotated many of the near vertical tracks such that the first edge of our graph network is parallel to the x-axis. So this is just a very simple diagram of the rotated tracks. You can see like the vertical tracks being rotated. Another aspect to note here is that the tracks actually follow a parabolic shape rather than being linear. So one thing that we are considering is to change our model setup. However, this does justify the fact that we are using a sort of correlated noise within our Kalman filter, and that being the OU process, because the model is not strictly linear, it is slightly parabolic. Okay, so this is post-rotation of the track candidates. So after applying that rotation within our Kalman filter, we can see that candidates were extracted uniformly at all 5, so that kind of fixed that problem. So without rotation, we see about 35% extracted tracks, but with rotation, we see 62% extracted tracks. We also computed the track purity and particle purity, and we made a cut of that. Our extracted tracks must be greater than 50%, and the distributions for that are plotted here. They are reasonably high for a first preliminary sort of result. And computing the track reconstruction efficiency, we yield a preliminary result of greater than 90% efficiency for tracks with PP greater than 1 GeV. So that's quite promising. A sort of sanity check here is that for the extracted tracks, we do expect a uniform distribution in chi-squared values when calculating the Kalman filter track fit, and the chi-squared values can be shown here. However, we do have a massive peak at 1, and that kind of suggests that we have overestimated our errors. But this is something that we're working on, and it's still being investigated. So the sort of ongoing and next steps for this project is the handling of shared hits. So here's a good example of shared hits and intersecting track candidates. So we want to be able to sort of identify these and leave in the shared hit and extract these two tracks separately. The next sort of step would also be to continue working on the community detection part of the algorithm in the track splitting stage. We'd also want to implement some sort of stopping criteria. So the quality of the remaining networks needs to be sort of assessed and terminate the algorithm after a certain number of iterations, and also continue with performance studies and testing. So this is the very beginning of this project, and we would like to improve it a lot and also extend it to the barrel region as well. So just to summarize then, so this approach developed here is unique, unlike a lot of the traditional approaches where we normally see multi-layered perceptrons being trained. The graph network is allowed to learn the local track parameters by iteratively resolving ambiguities. A preliminary result that we have is that the track reconstruction efficiency is greater than 90% for tracks with PT above 1 TeV. And the main sort of take home from this is that the importance of the Kalman filter for both the information aggregation and the track extraction, which is a very unique approach. And finally, just that we need to also evaluate how this approach works in denser hit environments and extend this to evaluate the performance of both the algorithm on the NCAP and the barrel regions as well. And yeah, that's everything.
Thank you very much. It's a very interesting presentation and yeah, very inspiring. Let's talk some for questions.
Monte from Monte, and thanks for a good talk. So I wonder how significant the OU process is in the material interaction.
Yeah.
I have not seen someone considering the OU process in the material interaction metrics. So
I don't think I have any metrics on, but just to give you an idea, when we developed the toy model, we didn't use any OU process. We were still able to extract track candidates fairly easy, but again, this was just a very simple setup with like 70 nodes and 7 tracks. But I think the OU process is fairly significant, because you can see better in these plots here that a lot of tracks can't be modeled using a linear setup and a linear extrapolation. We do need some sort of addition to our model. One thought that we did have was to incorporate into our track state vector the curvature and other sort of parameters such as the angle or the radius or things like that. But then the problem with doing that is that you kind of add additional complexity to your Kalman filter matrices, and you get that additional computational overhead that's not necessary. So by doing it this way, you kind of implicitly model that anyway, and it works quite well. It's quite efficient because it's a correlated noise. So you can tune your hyperparameters in the OU process, and that kind of models that sort of constant drift.
okay.
Thank you.
Alexis from H2IT. I didn't quite understood why do you need the Gaussian mixture reduction step before your Kalman filter step?
So this step before the Kalman filter.
Yeah.
So particularly within dense regions, this is quite important because of the fact that you have so many edge connections, and if you can prune any edge connections before doing the Kalman filter, it's much more efficient because you can get rid of obvious outliers easily with clustering like similar edges together. That's the sort of main aim. It just reduces an additional computational complexity when you're doing your Kalman filter.
Okay. Yeah. Otherwise, the Kalman filter step would be too long.
Yeah, because then you would have to introduce combinatorial Kalman filter, and that's just.
Sorry, are you hiding the combinatorial effect which you have in the multi-components of your GSF? Oh, it's not GSF, but your Gaussian mixture.
Yeah, so that's something that we need to assess. So we need to have a look at like the time complexity and things like that, which we haven't done as of yet. But yeah, that's something we need to consider.
Paolo, fascinating talk. We should have a 2-hour session in which we really go through the slides and understand it. I hope we can do that this week. But I have a question. Actually, a proposal really, because the reason that you are forced to collapse the mixture is, as you say, because you have too many connections out of any node. But if you were to run your filter just after let me say the GNN for ITK classifier, then you would have a fairly pure graph to start with, and then you can run it and not collapse at every iteration, collapse into one. But you could go like you could really use the power of the GNN to propagate information around. You could follow the tracks for 8 iterations, for example, and then you cover the entire net, the entire detector. So I think we need a 2-hour discussion.
Any other questions?
Yeah, that was really fascinating. Thanks. Can I take the bait and ask you to say a couple words on how you do the community detection?
Oh yeah, sure. I do have a backup slide on this. Okay, so this is an example of the community detection. Essentially, it's a partition of the network by identifying closely connected nodes based on another distance metric. So it's another sort of mini algorithm within my algorithm, and each color represents a different community. So within this very small subgraph, this starts off as one community. We then apply the community detection algorithm with your sort of threshold distance, and then the algorithm on its own identifies closely connected components. And you can see here, it works really, really well with a very small subgraph. It's not completely perfect because obviously you have this tiny fragment here, but that is essentially how it works. Yeah, and you can tune your distance, and you can feed in a sort of fast lookup table for different parameters and different distances, so you can train it offline as well. But yeah, this is something that we're working on, and it's not completely perfect at the moment.
More questions?
It's so interesting. I like it. I really like it. So for your Gaussian mixtures, though, you have to do the bookkeeping, right? You have to you need to kind of remember which component represents which node. So there's some whatever outside or attached labeling to the mixtures, which at the end makes it different from a Gaussian sum filter, where you don't care which component is taken because you just weight them. Now at the end, that's what I thought. There's the hidden combinatorics is in there. It's kind of, you could run it almost as a combinatorial filter when you walk through the labels.
No, so the one thing that you missed is that after the clustering is done, the remaining components are then merged into one single component,
which gives you the direction for the next.
Yeah. So in that sense, we don't need the combinatorial.
Just to be
Last
sure.
question.
Just to be sure, I understood. So you start from when, for instance, when you take the TrackML NCAP, the graph that you start from is a fully connected graph.
So yeah, so we start with this one, which is the end cap. And then we form all of the hit pair connections using a classifier that we built. And that's one massive graph. And then we apply the CCA, which gives us all of these separate manageable ones. Again, they do have dense edge connections that are going in every direction, but they are more manageable than that one initial graph. Does that make sense? And then we start the iterations. So on all of these separate mini manageable graphs, we then apply our Gaussian mixture reduction and then the extrapolation, and then we do the track splitting.
Okay.
Okay. So I bet we're going to have a lot of discussions offline. Let's thank the speakers.